All right. So you know how to do this. You just don't know what the notations are. So that's the big thing about today. So really and truly, let's take a note real quick. Yeah, let's do that. So again, this will be lesson 16, which is just representation or representing reflections with transformation. So again, same stuff you've been doing. It's just going to be different notation. So again, that's representing reflections with transformations. It's not too many notes, but a couple of notation purposes. When we're talking about rotations, we know rotation deals with some type of degree. So your representation of that is going to be a capital R. And then as a subscript, it's going to be in parentheses. And it's going to give like a point. So typically we'll do 0 to represent the origin, but it could be around any point. We'll start at the origin though for now. And then it'll be some type of degree. Hey, thank you. Yes. Okay. There really are. So it's going to be a capital R with a subscript of a parentheses. Typically, it'll give you a point or a letter. This is like the letter O. So this is a letter. Can you please both? Shh. So let this be the letter O just to represent the origin. So that will represent the 0.00. So that's a letter O that represents the origin. That's typically what you'll see, but you can do rotations around any point in the plane anywhere. But this will be our focus. And then it'll be a comma, and then it'll be theta. Remember, theta represents the degree of rotation. Bless you. So beforehand, bless you again. Beforehand, we used to say it was a rotation by a degree of whatever. Well, again, I tell you this all the time. Mathematicians are lazy, and we come up with symbols and letters to write the same sentence in symbols. Right? So this would actually represent the same thing as a rotation around a degree of something. Right? The other thing you need to know is reflections for today. So for reflections, it will use the lowercase r, and then it will just have a line. So this L here represents a line. Sometimes you might actually see this called the x-axis because that is a line. Sometimes you'll see the y-axis because this is a line, or some other random line. Another line that typically people like to use, but again, you won't see it called, like we know this right here is y equals x. This is a parent function of a linear function. But we're not going to say y equals x here. What instead, you'll see this actually called the letter L. And they'll say line L we want to reflect over, or line x-axis we want to reflect over. It's subscript. Yeah, subscript. Both of these are subscript. I just try to write it big enough so that you could see it as well. But these are all subscripts. I'm not going to count off if you accidentally write it on the same line. Like, that's not a big deal to me. But for notation purposes, this is what you'll see in your textbook. He might not able to read any of the letters, notations, or understand what was just written. All right, so this is going to be the same questions as asked last week. It'll just be in this notation here. Okay. Are we ready to look at some examples to see what that means? All right, does everyone have this down? Okay. So go back to your opening exercise ABC. Got it? All right, so this one here, it's going to ask you to find a transformation around the origin. That's what the little O is. 45 degree with a 45-degree rotation. So beforehand, you were given a complex thing, like you were given, I don't know, 1 minus 3i or something like that. And then we were able to calculate what the degree of rotation is. Here, I'm telling you what the degree of rotation is. Now, can you go find out what this guy is? So that's basically what we're going to do. And it's going to represent some random complex number z. We don't care what z is. It's just going to be this at the end of the answer. So what we're going to do is we're going to start off by trying to figure out what the complex number is at a 45-degree rotation. And the best way to do that is to start off here with our polar form of cosine theta plus I sine theta. Right? And since theta is given to us, we're now going to plug this in to figure out if we can figure out the rectangular form. So this will now be cosine of 45 degrees plus I sine of 45 degrees. And how do I figure out what those coordinates are? What do I do? How do I figure out what good? You need your no. We need our not calculator. You just told us. You need the paper plate. You need your unit circle. So if you go to your unit circle that we created and we go to 45 degrees, what is the cosine of 45 degrees? Which remember, that is the x value of the coordinate. Perfect. Square root of 2 over 2 plus I. What is sine of 45? Also square root of 2 over 2. That is what will produce a 45-degree rotation around whatever your z is. So your final answer here would just be the square root of 2 over 2 plus I square root of 2 over 2 times whatever complex number they wanted to give us. This would guarantee a 45-degree rotation of whatever point I choose. Okay. So again, a little backwards from what we did last week, where we gave you this and then you calculated it for me. Now I'm giving you the degree. Can you give me the complex number? Questions on the math here? That's it. This is the answer. Let me box it up in a pretty red square. It is. It is. The only difference is exactly, which is, I feel like most of these lessons. But the only difference from last week is last week I gave you this complex number, and then you did like the tan inverse to calculate what the degree of rotation is. This go around, I'm giving you the degree of rotation. So we're going to start off with our polar form and change it into our rectangular form. Both of them are technically complex numbers. And then whatever this is, we're just going to put z next to it to represent whatever my z was. If I multiply this to it, it'll guarantee me a 45-degree rotation. Does that make sense logically? All right. Do y'all want to try B on your own? Ooh, let's think about that. If you are at negative 45 degrees, what quadrant do you think you'll be in? Quadrant 4. What degree is negative 45 degrees? 315. So even though this says negative 45, you need to look for 315 or know that those are the same values. Are we cold, hot, content? I'm freezing over here. Okay. Cold, content. Yeah, sorry guys, y'all lost. Probably by like 2 votes. Let me know when you are done so we can check it. That's when we would have to plug it into the calculator. But on all the SAT and ACT questions I've seen, if it's something that falls on a unit circle, it'll be written in this fraction form. Now, a way you can get around that and still use the calculator is whatever decimal you get from your calculator, type in the fractions, and they should be the same decimal, then you know you got the right answer when doing test prep. I think y'all got what SAT this week or next? Next week. So think of that's a pedagogue question. I have no idea. I thought they moved it. Yeah, I think they moved it so it would be on the same. But that'd be a pedagogue question. All right, do we all have an answer? Anyone need more time? Well, that matters. Yeah. If you're using the calculator, make sure you're in degrees. Good point. No, I'm just if you needed it. Well, no, you want it in rectangular form, not polar. Caleb, you want it in rectangular, not polar. You should express it in polar form. Oh, the movie. I guess that is a song. Makes sense. Are we good? All right. So again, what you want to do is you want to start off with your polar form. It doesn't matter. Note that 315 negative 45 would be the same result. You could technically put 675 degrees in there and you still get the same results because the circle again keeps um, going around and around, so it keeps landing on that same point, and you can keep adding 360 or keep subtracting 360 from that result every time. So what you could have done here, rather than trying to figure out where negative 45 is, you could have took theta here and added 360 to it to get you to 315 as well, just so you can see where you landed. Okay. Regardless of where this is the same as 315, but so what's cosine? Square root of 2 over 2. And what's sine? Perfect. With the I. Perfect. But notice you said, isn't it the same thing but negative? The only thing that was negative was just the y value. So my final answer should look like this: square root of 2 over 2 minus square root of 2 over 2 I times the z. Right? Don't forget to put the z at the end because that is technically what you're trying to produce. Right. Any questions there? Go ahead. I was just thinking that as I wrote it, to me, it's not going to matter. And I kept the I here because that's how the polar form was. But in rectangular form, we're so used to A plus BI that I think the I should go at the end, but I don't think it's going to matter. I wouldn't take off. That's my thing. The only thing I would take off if this wasn't in the right form, make sure it's the real and then the imaginary parts. But when you're looking at a multiple choice question test, um, with the I here, multiplication is commutative. So the order is not going to matter in a technical sense. Any other questions there? All right. Now, when we look at C here, notice this is a little r. So that represents the reflection. So we're looking at the reflection of something. We need to go, all right, if I have some random point here and I want to reflect across the x axis, that's going to be over here. We have a definition for that. What definition of z reflects across the x-axis? Uh, okay, okay. No, not imaginary or the real. No. To what? No. Huh? The conjugate itself. We learned that a reflection across the x-axis will just be the conjugate itself. So you don't have to do any multiplication. We just have to take whatever the z is, find its conjugate, and then regraph it, and we have the reflection. Right? So even though it's not asking what the conjugate is, and it's asking what the reflection of over the x-axis is, that is the same thing because we learned that the conjugate is just a reflection across the x-axis. By chance, do y'all remember what a reflection over the y-axis is? The negative conjugate or the opposite conjugate, either where it works. So, huh? Opposite, I think we're good. Reverse, I don't know, because reverse can mean a lot of things in math. But the go across the y-axis is either opposite or negative version of the conjugate. Good. That wasn't a question here. I just wanted to see if y'all remembered. All right, let's progress through. All right, so here is our discussion. What happens if that reflection right there is not an x-axis or a y-axis, and it's a random line? All right. See that lowercase r there? Well, it's kind of there. So it's saying I want to reflect this point across this. So you can kind of guess. I mean, roughly, it's probably going to be about right here, right? Kind of if it's reflecting completely, I'm thinking it's going to be about right there. That's going to be a guess. But we need to figure out what do we need to multiply by to get that perfect rotation, right? So if we keep on going forward with this and we take a couple of steps here, and let's say for starters, this is y equals x. It does give us that fact. And with y equal x, I do know that this would be 45 degrees. Okay. So let's start there. Hold on, let me think. Yeah. Okay. So 45 degrees from here would probably roughly, I think, land us about right there. We roughly said that this was 45 degrees. Then whatever that space is, will put us there. Okay. Not exactly in the area that I want. But how do I even get to this point? Well, if I'm going to go 45 degrees from this point, if I'm going to go 45 degrees from this point to this point, what direction is that? Clockwise, what's the degree going to be? Negative. So I need to go, to start off, let's go negative 45 degrees to get to this point. And so that's going to be, for your notation purposes, this guy right here. And we just calculated this on the opening exercise. What is a rotation negative 45 degrees? Okay, yes, but we did all the math. What was the coordinate? The complex number that minus the square root of 2 over 2 I times z. So whatever my z is, because I don't know it, I need to multiply it by this guy to make a 45-degree rotation. That's my first step. Because I'm trying to get here. Oh, because it's y equals x. If you recall, y equals x just means that the slope goes over one, up one, over one, up one, over one, up one. So what it does, it splits a 90-degree coordinate plane directly in half. So this would then be 45. Because so that's what I was telling you in the notes a while ago. It's not going to say to a reflection of y equals x. It's going to give y equals x a name. It's going to give it, and it gave it a name of L. So since this is y equals x, and I know it is, it's a 45 degree here and a 45 degree here. So what I want to do is I'm trying to get this z to reflect over this L to get to this point. And I don't know exactly what this coordinate is to know how much degree it is. If I knew what this coordinate was, let's say this was 80 degrees, then I could easily just go, all right, well, this is 20 degrees here. So let's go 60 degrees there. So I'm also 20 degrees there. And I'd calculate my answer. But you don't know that. So the math behind it is we have to first go 45 degrees clockwise, and we got the math to do that. But that lands me about right here. I'm trying to get here. So the next thing I want to do is actually do a reflection across the x-axis. So I'm now going to take whatever this is. Let's call this z1. And I want to do a reflection over the x-axis. And if this whole thing is z1, I can basically just do what? I can make it the conjugate, right? So technically, this is what I'm doing. I'm going to do the conjugate of what z1 was. Well, the conjugate of z1 was the square root of 2 over 2 minus the square root of 2 over 2 I z. Yes. Oh, you're right. Thank you. It should be a lowercase. Thank you for catching that. All right. So again, that was a z. By the way, I rushed it. What's up? What's your question? No, so this is the conjugate of this. I didn't get to write my line across. Well, what's the conjugate of the square root of 2 over 2 minus square root of 2 over 2? Very good. And then we don't know what z is, so it'll just be the conjugate of that. So this is where we're located right now. On what part? Of z1. So this isn't the conjugate. We don't know what z is. We just knew at first, if I multiply by this complex number, it will give me a 45 degrees clockwise, as we saw in the upper exercise B. I'm now needing to figure out what it's going to be to reflect across the x-axis. Well, we saw if we just take the conjugate of it, that will give me a reflection across the x-axis. So I had to take the conjugate of the entire thing. That's why there's a line over the entire thing. Here, it's super easy to calculate what the conjugate is. We just got to change the imaginary part. The issue is we don't know what our original point was. So it just stays as z's conjugate. So this will be the conjugate of the reflection of 45 times whatever the conjugate of the z is. But again, that's only putting me here. I still need to get here. And to do that, this right here would produce another 45 degrees. But now I'm going counterclockwise. So instead of a negative 45, I would now need to calculate, and we'll call this whole thing here Z2. That'll be what that point is. So if I do a rotation around that same origin of 45 degrees to go back to this original reflection point, I can then take this and I have to multiply it by whatever the rotation is. What is the rotation for a 45 degrees on part A of the opening exercise? So if I take whatever this is and I multiply it by another square root of 2 over 2 plus square root of 2 over 2i to this mess here, it will give me another rotation of 45 degrees, landing me where we'll call this Z3. Now we can't just stop there. We need to do the math to figure that out. And how do I multiply two complex numbers? Distribute. Very good. So we can't be scared of fractions and we can't be scared of these radicals. So we got the square root of 2 over 2 times the square root of 2 over 2. What's that going to produce me? 2 over 4. Perfect. Square root of 2 over 2 times square root of 2 over... Good. What's the square root of 2? So when we multiply fractions, we multiply straight across. So you do numerator, numerator, denominator, and denominator. So what is the square root of 2 times the square root of 2? So what's the square root of 2 times the square root of 2? Oh, 4 times 4. So what's the square root of 4? 2. So the moral of the story is if you multiply two radicals together that have the same radicand, the square root, the radical just goes away and you're left with the radicand, which is in this case 2. Radicand being the number inside the radical, and the radical being what y'all call square root or division sign or a check mark or whatever this being. Right? And so then if we do it again, what's the square root of 2 over 2 times the square root of 2 over 2i? Very good. Then what's the square root of 2 over 2i times the square root of 2 over 2? 2, 4i. And then what is the square root of 2 over 2i times the square root of 2 over 2i? That's like a tongue twister. Just do that 5 times. Very good. All right. Now, what do we know about I squares? So this whole thing is really a negative 2/4. So what is negative 2/4 and 2/4 going to do? And then what is 2/4 plus 2/4? 1/4. So this ends up just being I and then the Z conjugate. So the moral of this story is if you want to reflect this over this line, all I have to do is figure out what its conjugate is and multiply it by I. That's just pending that's a 45 degrees. Now, this doesn't always work. But if you are reflecting over just y equals x, instead of having to do all of this process, you can just recall that I can just figure out what the conjugate of z is and multiply it by I. I know, a lot of work, right? Questions? Don't even know what to ask. Yes, sir. That's a good question. Yes, sir. You can. All right, let's do some more. I don't expect you to be experts today, just by Thursday. Oh, did I not give you time to finish? All right, so in this exercise here, it's now telling you what z was. It was 1 plus 5i, right? So there's a few processes here. It don't know what would be the best situation. Do I need to show you? I need to show a lot of things, but do I need to show this? If I go back to what we just did here, all this mumbo jumbo, right? Do you agree with me if I tell you what Z is, that you can just use this formula in orange? Or am I going to need to put it back in here and do all the work, get an answer, do what the answer in orange is, and show to you that they'll give you the same answer? Okay, so that's why I'm thinking now that we have our equation, let's just use that. All right. Because if you don't believe me, I would have to plug it in for all these Z's here just to show you they give you the same thing. So if you want to see that, just come to tutorials for that. Huh? I know I'm totally down for it, but I feel like I would have about 3 people understanding what's going on. So with that being said, now that I know I'm reflecting over line L, which was the reflection over the X, sorry, not X, but like this Y equals X, well, all right. If I want to reflect over line L, and I know that line L is Y equals X, knowing that fact, I can now just go figure out the answer, which is just I times the conjugate. All right. So that's what I'm going to do to figure out what the answer is. Now that I know that Z is 1 plus 5I. So that's going to be I times, what is the conjugate of 1 plus 5I? Okay. And then now I'm just going to distribute. So I times 1 is I, and I times negative 5I is, all right. And what do we know happens with an I squared? It's going to change the sign so it becomes a plus 5. The only thing is I got to write this in the correct order, which in this case is 5 plus I. So to give you an idea, now that you have this answer, does everyone have this written down? I'm about to erase it. That's why I'm asking. Okay. So that we have our nice equation, we get our nice answers, right? But again, this only works if the line of reflection is Y equals X. I'm going to show you different ways on how you can calculate all of them. But before I get to that, I want to show you how accurate we might have been. All right, so here we see that this first point was 1 comma 5. So I'm thinking these things are going by twos. So this is 2, 4, 5. Here's about 1 comma 5, right? That's what that first point was. We then calculated that the answer was what? 5 comma 1, 5 plus I? Is that what we just got? All right, so if we go 2, 4, 5 comma 1, that lands me right there, which definitely looks like a reflection over line L. So we know that our previous work to get to that formula worked out. The reason I don't just give you the straight up formula, because it only works for this situation. You need to be able to use what I just did to calculate for any of them. All right, so let's do that now. If it's Y equals X, because we've calculated it. But now what happens if it's not 45 degrees? What if the line is, I think, what's the next one? What if it's 60 degrees? Yeah, if it's right in between. What if line L is not Y equals X and it's like a 60 degrees right here? 30, right? Yeah. What do we do in that situation? Because I times the conjugate will not work. All right. You can go ahead and cross out number 2. We just pointed out we're not doing proofs. Yes, sir. All right. So number 3 brings up the next discussion. We now want to find a formula for the transformation of reflections across this line L that now makes this 60-degree angle with the positive x-axis. So we're going to find formulas to represent each component of the transformation and then use them to find one formula that represents all transformations. All righty. So here we go. So here is what's going on. Here's a graph. And it's no longer y equals x, but it says that this has a 60-degree rotation, right? So I don't quite know where my point is. Let's hypothetically say it's on this side, and I want to get it on this side, right? So this is where it is. This is where I need it to be. It could be opposite of that. It could be way over here, and then I would want it way over here, being a perfect reflection, right? That's what I'm trying to produce here. But I need a formula so I can calculate all of them. So to start off, just like before, if this point is located here, if this is 60 degrees counterclockwise, the first thing I'm going to want to do is go 60 degrees counterclockwise. So it's going to be the exact same process, right? So I'm going to do the work here. And then on the other side, I'm going to develop an equation that works for all. Okay. So for us, I need to produce a reflection around this origin, not a reflection, sorry, a rotation around the origin at negative 60 degrees. Well, if you saw what happened on the first question or the discussion, it was basically a rotation negative 45 degrees. So what we can say is I have an equation where it'll be some rotation around the origin of negative whatever the theta I give. So this will be the first step to find all of them. And we're going to produce this equation by just finding this one, right? Because we're seeing connections. It's always going to be the negative of whatever the theta is given to you. You follow with that first step? Go ahead. Then it'll be positive. So this will represent not that it has to be negative, but it's opposite. So if you're given a negative degree, then you're going to be using a positive degree. That's a good question. Yeah, because what if the point's over here on this side and I'm trying to reflect it on that side? Now I'm going to want to go positive. So that's a good point. Thank you. I forgot what I was talking about. Oh, now in this situation, it's going to get a little different. I need negative 60 degrees, which is the same thing as what? 300. Very good. So this would be the same thing as if I asked you this question. The only issue is we haven't produced this yet. So let's produce this. This would be cosine of 240 plus I sine of 240. Go ahead. No, it's supposed to be 300. Why did I write 240? Ugh, I do apologize. Where 240 come from? Did someone say 240? Oh, that's where it was. It's 300 because, again, if you take this and you add 360 to it, you'll be at 300. Or if you go 6 degrees clockwise, you land right there at the 300 mark. Thank y'all for catching that. This process would not have worked if that's what we were looking at. Oh, man, it's so hot in here. Yeah. All right. Do we even have a 240? We do have a 240. So what is my coordinate at 300? Right? We all agree with this? So this is the same thing as that negative 60. And whatever my z is, that's what I'll multiply by. Okay. So that's our first step. So our first step will be calculating whatever the rotation of the negative theta is and multiply it by z. That will work out every time. That's what we've done every time. Now that I've rotated this 60 degrees, I now wanted to reflect it across the x-axis. So I now want to reflect across the x-axis. And when I did that, what did I do to do that? Yes, I used the conjugate of my previous answer. All right, so that's what's going to happen here. So to get my answer, I would then, yeah, a straight line over it. Well, I haven't done it yet. I just did the conjugate. So, okay, let me work it out. So the conjugate of that would be a plus. So that'd be 1/2 plus square root of 3 over 2i, and then a conjugate on top. So in applying it to our I did to get the conjugate of the whole thing. So the conjugate of this one was just a plus. This one, I don't know what it is, so it just gets a little line above it. So with that said, once I calculate what this is, I can just produce its conjugate. So I'll just put a bar over all that. Okay. All right. The last thing I did is then I used the actual theta to produce my point of interest. So this will now be a rotation of 0, comma, whatever my original theta was. So after I found the opposites and then I did the conjugate of it, I'll now use the actual theta. So I come back over here. This now produces a 60 degrees. So I need to figure out on the side here, what is cosine of 60 degrees and sine of 60? I got to figure out this guy. What is this? Perfect. So that's the guy that I now need to multiply by this guy, which happens to be the exact same thing. Ain't that bad, guys. After that, how do I multiply two complex numbers? Distribute, FOIL, 1/2 times 1/2. 1/2 times the square root of 3 over 2i. I, good. Square root of 3 over 2i times 1/2. Square root of 3 over 2i times square root of 3 over 2i. All right. So then I know a couple of things. This 3/4 I squared is going to become a negative 3/4. A 1/4 minus 3/4 is not negative 2. I got your idea. Negative 2 over 4, which is just what? Which is just what? Negative 1/2. Very good. And then square root of 3/4 plus the I. All right. Square root of 3/4 I plus square root of 3/4 I would give me. Good. So this will then give me 2 square roots of 3 over 4i. Now, what do you see about this 2 and this 4? Don't cancel out, but it can reduce, right? What can it reduce to? To 1/2. And all of that will be multiplied to z's conjugate. So notice here, I didn't just get an I times the conjugate of z. I got a little bit more going on times the conjugate. But this formula right here will help you produce the work you need to get to your outcome. There we do. We just end up getting 1 or just a 1i. According to what we see here, we started off with 45 degrees on the discussion. Because it was y equals x, so I knew that it was going to be 45. It didn't actually give me 45. I just knew it would be 45 because it's a y equals x equation. This one that we have here is we don't know what the equation is, but we know that the degree was 60. So that's your answer right there, by the way. That's really all that I got. Um, that's it. I'll be here after school as well today. Might be taking a nap with you, but I'll be here. Ugh. You enjoy the rest of the day, guys. That's a negative 1/2 plus square root of 3 over 2i. Negative 1/2 plus square root of 3 over 2i because the 2 force reduced down. times the Z conjugate. It's good. Yeah, feel that. This here, positive square root 3 over 2i. Z conjugate. Simple enough.